This is the most powerful electrical force on Earth. Around the world, lightning strikes more than 8 million times every day, 6 times hotter than the surface of the sun, releasing as much as 1 gigajoule of energy. It defies the laws of nature. Although it is known to be dangerous if you are in the wrong place at the wrong time, it is also the source for life. The combination of air, water, and electricity creates the ideal circumstances for plants to grow. In a thunderstorm, ambient air is activated by plasma that is formed by lightning. This activated air is brought into contact with rainwater, which causes the reactive oxygen and nitrogen to dissolve into the water. This creates plasma-activated rainwater with unique temporary cleaning abilities that finally settles into stable fixated nitrogen.
Plasma-activated water, this is water which is treated by plasma, typically in the air. After treatment by plasma, that became this water rich of many reactive oxygen and chemical nitrogen species, which possess quite long chemical activity, and they have even the biocidal effects. The beauty and the interesting part of the plasma activated water is that we can use it remotely after for some application, including agriculture one, for treatment of seeds, plants, using as a fertilizer, etc. We are dealing with the chemical characterization of the plasma activated water prepared by different plasma sources, because this is one of the very important tasks. We need to understand how to prepare the plasma activated water.
This is, for example, a detection of nitrites and nitrates in plasma activated water by means of ion chromatography. Here you can see the chromatograph of the plasma activated water, where we can see the peaks for nitrite and nitrate in the ion chromatography procedure. In our plasma activated water, which is made by the electric barrier discharge above the water surface, we can generate quite a high concentration of both nitrites and nitrates, as well as hydrogen peroxide. For these concentrations, we also measure quite a low pH value of about 2 or 2.5. So it means that this liquid is acidic.
Properties of plasma-activated water can change very significantly depending on the plasma source, gas, and also the contact of plasma with water. And in our group we are studying generation of plasma-activated water and possible applications in medical research and agriculture. And in our research we focus, for example, on production of plasma-activated water by using discharges which are able to transform water from bulk to micro droplets, and this aerosol is then in very good contact in plasma, and thus we are able to produce plasma activated water very efficiently.
And we also analyze, let's say, concentration of antioxidant enzymes, just to see whether the plasma activated water can cause some stress to the plants, which is very important. And we also not analyze even leaves, but generally from the seedlings, both parts, like roots and also the, as they said, above ground part, that means usually leaves and then the rest. And we also analyze, let's say, the roots, that we cut them, and we also did some measurement with fluorescent measurement, just to see, for instance, how the walls of the cell walls lignify. That means how they harden in time, whether, let's say, plasma activated water supported the growth of the plant. Because many times the properties of the plants which are affected by plasma activated water is not really visible. Like if you consider the plants, you see they are a little bit bigger, but not that much, but usually on macroscopically. But if you go microscopically, then you see many of the parameters improve, which cannot be seen by a naked eye. And recently we also started to combine the plasma activated water with arsenic, just to see like how much stress is, how much stress comes from the plasma activated water, or how much stress comes from arsen, and whether kind of this effect of arsen cannot be suppressed, or usually suppressed by using of plasma activated water, in case you have some kind of metals in the water.
You can imagine that if you have a needle, medical needle, and you provide a water through this needle very slowly, for example 1 milliliter per minute, then there appear droplets which fall down from the needle, and if you apply electric field, so you apply high voltage on this needle, the electric field changes the properties of surface tension of the water, and as a result, as you increase the voltage, the droplets become smaller and smaller, and at certain point the production of so-called Taylor cone at the top of the needle, at the nozzle, will emerge, and from this Taylor cone microdroplets will start to drip off. And these microdroplets can have diameter of several tens of micrometers. Then at certain voltage there will be not only spray but also corona discharge appears. So corona discharge or streamer corona can operate together with this spray, because there's a DC voltage and electric field is always high enough to form these microdroplets. We hope that with this technique we will be able to produce relatively quickly water which would contain high concentration of nitrates and nitrates. In our laboratory we are able to make a diagnostic of gas phase production species. For this purpose we are using either infrared absorption spectroscopy or UV absorption spectroscopy for species like NO, NO2, ozone in a gas phase, or nitrous acid, for example, in a gas phase. In a liquid phase we use colorimetric methods usually.
And we study in fundamental way, experimentally, these transport processes, for example, of hydrogen peroxide, ozone, and then different nitrogen species. And what we found out is that, for example, ozone, which is badly soluble, doesn't dissolve well, so it really helps if we make small microdroplets or aerosol of water. So that facilitates the transport. On the other hand, if we have hydrogen peroxide, it's very well soluble. It's so well soluble that often the limitation factor is the gas phase concentration. So we practically the water will take everything which is present in the gas phase as hydrogen peroxide will go into the water. And then these nitrogen species, the solvation of different types of nitrogen species typically leads to nitrites, NO2 minus ions, contributed by NO, NO2, but especially HNO2, which is a dominant source of nitrites. So then we get all these species in the liquid, and hydrogen peroxide and nitrite are really important in the sense of antibacterial action of the plasma activated water, because they can produce these peroxynitrites, which are really active antibacterial components. And by changing different parameters in the plasma, we can tune the composition and parameters and properties of the plasma activated water depending on the application. So either if you just want to do the disinfection, you tune it differently. If you want to have it as a green fertilizer, we focus mostly on this nitrogen species so that the water is really rich in nitrite and nitrate. Such plasma activated water typically shows some antibacterial or antimicrobial properties, so it can be used to disinfect surfaces, medical instruments, but also living wounds. it may have some other biorelevant properties. For example, it can be used to selectively treat cancer cells for future cancer or potential future cancer treatment. But also, this plasma activated water can be very much enriched of nitrogen species, from nitrogen from the atmosphere, making nitrites and especially nitrates in the water, so it can serve as a fertilizer for agriculture. So there is this antibacterial action on one hand, and there is this nitrogen-rich fertilizer on the other hand, and we can have also kind of both aspects combined in one type of plasma activated water, which seems to be very beneficial to promote the plant growth, for example. But the applications are different. There are several types. One of them is treating the seeds, agricultural seeds, to promote their germination. And indeed, soaking the seeds in plasma activated water facilitates or enhances the germination of the seeds. But it's not just that. Then the plant growth is somehow enhanced as well, especially the early stage of the plant growth. So the seedling and the first days and weeks of the plant growth are much improved and promoted, so the plants grow faster, they grow bigger. And even more importantly, from the point of view of economical benefit, the plants which are somehow treated with plasma activated water, either as seeds or already as plants which grow, they seem, based on several researches of our group but also different people's group, they can make more product, more agricultural yield. They make more seeds or more fruit, more products. So far in our group, we have tested more or less on a laboratory or small field scale. So doing really well-controlled laboratory plant experiments in collaboration with our partners of plant physiology, but also small-scale field experiments in outdoor conditions, and we are testing that, and repeatedly several years we have been testing those. The other challenge is to understand these mechanisms, to really be able to tune the plasma-activated properties from one tip or specific for application, if we want to treat only seeds or we want to promote the plant growth or to make bigger yield. And another big challenge is scale up to large volumes, because of course at low energy cost, because of course we need electricity to produce plasma, and we must keep the energy cost low and still make large quantities of water to be applicable in large fields. So the scale up is a big challenge we are trying to address. So we can reduce the use of fossil fuels, carbon dioxide emissions by fixing nitrogen into the water with the help of the plasma from renewable electricity sources, which can be small sources distributed in farms. So with no need of huge plants like the current technology of ammonia production by Haber-Bosch technology.
So the problem is, like, it's very difficult to say, like, which condition should be used for plasma agriculture. And the most difficult thing is, like, we usually work in a laboratory scale. That means we usually generate a very low amount of plasma activated water per unit of time. If you want to go to a field, people ask you to generate for the same time much higher volume of the water, which is very difficult with the usual, let's say, some kind of simple discharges. So you have to scale up your system. The scaling up is a problem in general, to scale it up, and also because if you scale up, well, also you need more energy. So then the question is it affordable for that kind of money when you scale up your system? So this is one of the problems of the plasma activated water, just to be competitive in a sense of energy consumption and of course the economy of these methods. So I think this is the most important.
Certainly, as always, I think that will be the energy cost. It will be for the market always important issue how much that cost. Well, depends, of course. Also, we need to define also the safety issues, possible toxicity effects in plasma activated water, which would really cause the for the market that would be not acceptable. So that certainly we also need to address that issues related to safety of the plasma activated water. Certainly, as always, I think that will be the energy cost. It will be for the market always important issue how much that cost. Well, depends, of course. Also, we need to define also the safety issues, possible toxicity effects in plasma activated water, which would really cause the for the market that would be not acceptable. So that certainly we also need to address that issues related to safety of the plasma activated water.
For major challenge for me is the upscaling to reach reasonable production rates of this plasma activated water.
So this is a device which is combining two phenomena together, cavitation or hydrodynamic cavitation and cold plasma discharge. The device is seen here. This is, let's say, a demonstration unit for 1.3 cubic meters per hour treatment of the water. It was awarded by several awards here in the Czech Republic because of its uniqueness, because of the large amount of water that we can treat. So we are starting in this unit with 1 cubic. So the power consumption of this device is 1 kilowatt hour per 1 cubic meter of the treated water. And this device can work in two modes. The one we call the direct mode. It means that the polluted water is going directly through this, which is not probably of interest for this project. And the other is that we can prepare so-called plasma activated water. It means after one or several treatments within this device, we produce a water which has some content of hydrogen peroxide, and this water can then be used, for example, for some flushing of contaminated surfaces in agriculture. The scaling was surprisingly simple and without any problems, I think, to, let's say, surprise of all involved people.
This device combines two unique technologies: cavitation, which means we are producing a low pressure gaseous environment inside the liquid, in which we can easily turn on the discharge. So among the other technologies, we can produce more plasma or larger volume of the plasma inside the liquid at the favorable conditions, where we can produce OH radicals, hydrogen atoms, oxygen atoms, and then finally it combines into hydrogen peroxide, which can be very easily dissolved into the water due to the combination of the cavitation stage of this device.
What we sell is machines that can produce plasma activated water on site at customer's location. Our machines can produce 30 moles of nitrate per hour, and those are 15 kilowatt machines. And one machine can provide, depending on the type of crop, a half a hectare or up to 2 or 3 hectares of cultivation with nitrogen fertilizer. The farmer needs about, depending on the crop type, 10 millimoles per liter. So we provide it with a fertilizer solution that has 10 times or 20 times that much nitrate in it. But we make sure that there is no nitrate in it because the growers don't want that. They see a nitrate as toxic. And indeed, in higher concentrations, it can be toxic for plants. Specifically, if you grow the crops on hydroponics, then you only have water with nutrients, and then those components can interfere. If you grow on soil, then the soil has a buffering effect, and that can then the effect is not that large. We can currently not compete with the traditional synthetic Haber-Bosch process for nitrogen fertilizers. So we are more expensive. But if you look, for instance, to the organic market of growing vegetables and growing food, organic fertilizer are much more expensive than the synthetic fertilizer. We are competitive in the market of organic fertilizers. So that offers an opportunity for us and a challenge at the same time. But as you probably know, the industry which is producing ammonia, the Haber-Bosch industry, wants to shift to a carbon-free production of ammonia, and then they want to use hydrogen for that, the so-called green Haber-Bosch process. If you compare our technology with green Haber-Bosch, then we are practically the same, and within 1 or 2 years we will surpass them, that energy efficiency.
So this is based on this publication, Cherka. So in terms of energy consumptions in megajoules per mole, and non-thermal plasma is the blue one here, and the theoretical limit is somewhere down here, which converts to gigajoule per ton of nitrogen, something like I think this is like something like 10, because especially when comparing with Haber-Bosch processes, this is the typical parameter which is used, gigajoule per ton of nitrogen fixed into, in the case of Haber-Bosch is of course into ammonia, but in case of plasma it's mostly into nitrate.
For our fryer machines, they're the machines that are specifically built for fixating nitrogen as a fertilizer. We make sure what comes out of the machine doesn't have any disinfecting properties. So it's only basically nitric acid what is coming out of the machine. When we look at the other applications, then we do want the other species. Then we do want hydrogen peroxide. We do want some nitrate to allow the plasma activated water to react and disinfect the thing you want to disinfect. So there are different machines. If you want to disinfect with plasma activated water, we have different machines for doing that than only pure for nitrogen fixation.
So it's basically based or driven by the application, by what we want to achieve, what is the desired effect. Then you can tune the process to make either peroxide, nitride, or nitrate, just nitrogen fixation for fertilizer. Yeah, that's actually a big advantage of plasma technology, that it can be relatively easily scaled to small scales and even large scales, but also can be tuned to different purposes, different objectives.
Yeah, that's correct. Yeah.
At the moment, we have few machines and we can produce around a few thousand liters per day. Yes, we are at the beginning because the technology is new, no regulations. And we need to find out where we stay, where's the position. And yes, but we need support, from governments around the world. We need support from universities. You need support from researchers because they have the knowledge, they have a lot of experience already. And if there is a way to make a combination, between all of this. So yeah, we are happy. A lot of people around the world, not all of them, but a lot of them already understood that climate change topic is not something which we should ignore. So this topic is really, really in focus. And I don't think that this topic would go away in a few weeks, few months, or maybe in a few years, because we need to find a way together. So all humans, I mean, to find new solutions, innovations, maybe to try new ways which are not exist at the moment. And there are some issues, some problems. As you told me, around the world we have pesticides. We have a big problem with greenhouse gases. We have problem with pesticide in groundwater. We have as well commercial problems for the farmers because they have a problem to pay this huge amount of money for chemical fertilizers because the price just grew up the last few months and few years. Because we are at the beginning, you asked me about the future. Let's see what it brings because there are a lot of possibilities. So as I already said, there are medical applications with plasma activated water. There are wound-healing topics. Disinfection is a huge topic around the world, especially after COVID or during the COVID. But on the other one side, there are also topics with wastewater. So this topic still exists since long time, and there is no way to say, okay, this topic was going away or whatever. So it still exists. So wastewater is a topic because of the climate change.
One day, sooner or later, plasma-based agriculture will be one of the main agriculture worldwide and will progressively push away the current fossil fuel-based Haber-Bosch technology for ammonia and ammonium nitrate sulfate production as artificial or chemical fertilizers.